Welcome to DAR Tutors for online and home tuition. In this video, we will explore the fundamental concepts of mathematical modeling, which is a key topic in the IB Mathematics Applications and Interpretation higher level curriculum. By the end of this session, you will be able to, first, apply the four-step modeling cycle to simplify and solve real-world problems. This cycle is the structured approach we use to build models. Second, construct and analyze linear models, including exact and approximate cases. Understanding linear models is crucial because they are simple and yet powerful for many situations. Third, create and interpret piecewise linear models, which are used when relationships change at certain points. This allows for more realistic representations of complex scenarios. And finally, we will use systems of linear equations to determine the parameters for quadratic, cubic, and other nonlinear models. This process allows us to fit a known function type to a set of data. These skills are not just theoretical. They are essential for interpreting and engaging with the quantitative world around us. Let's begin by introducing the core idea of this chapter. What is a mathematical model? It's a simplified representation of a real-world system using mathematical concepts and language. The purpose is to describe, understand, and predict the system's behavior. It's important to remember that real-world problems are often too complicated to describe perfectly. So, in mathematical modeling, we always simplify by making assumptions. These assumptions allow us to create a model that is manageable to work with and that can provide useful, approximate solutions. The development of a mathematical model is a structured, iterative process called the modeling cycle. Let's break it down into 4 key steps. Step 1. Posing the problem. This involves clearly identifying the problem, defining your objectives, and most importantly, making simplifying assumptions. These assumptions are crucial because they reduce the complexity of the problem to a solvable one. Step 2. Developing the model. Based on your assumptions, you'll choose a type of mathematical function, perhaps linear, quadratic, exponential, or piecewise, and construct a formula or equation that connects the relevant variables. You must also consider the domain and range of your model to ensure it makes sense in the real-world context. Step 3. Testing the model. Here you compare the predictions from your model against real-world data or observations. For example, does your model for car speed accurately predict how long it takes to cover a certain distance? If there is a significant discrepancy, you must go back and refine your model, possibly by revising your initial assumptions. Step 4. Applying and extending the model. Once you're satisfied with your model's accuracy, you can use it to answer your original question or make predictions. Reflect on its limitations and consider how it could be extended to be more general or accurate. Remember the famous quote by George Box, "All models are wrong, but some are useful." To solidify this process, let's work through an IB-style problem that uses the modeling cycle. A house is to be built along an isolated road. It needs to be connected to a water access point W and a gas access point G. The road is represented by a straight line. W is at position 0 and G is at position 2, both in kilometers. Let the position of the house be x kilometers. Our objective is to find a model for the total length of pipe L in terms of x, and then use it to find the house's position that minimizes this length. First, we pose the problem. Our objective is to find the minimum pipe length. What are our assumptions? We must assume the house can be built anywhere on the road. We also assume the pipes run straight from the house to each access point. Next, we develop the model. The length of the water pipe is the distance between the house at x and the water point at 0. The length of the gas pipe is the distance between x and the gas point at 2. Since distance must be non-negative, we use the absolute value function. The total length L is the sum of these two distances. Now let's apply our model to answer the question. We need to find the value of x that minimizes L. To do this, we can split our absolute value function into a piecewise function based on the critical points x equals 0 and x equals 2. Let's test this by calculating L for a couple of points, as we might in the exam. First, if x equals 1.5, which is between 0 and 2, the model gives L of 1.5 equals 2. The total length of pipe is 2 kilometers. Second, if x equals 1, which is less than 0, the model gives L of 1 equals 2 times 1 plus 2, which equals 4. The total length is 4 kilometers. A sketch helps us visualize the function L of x. We can see a horizontal segment at L equals 2 between x equals 0 and x equals 2. Outside this interval, the graph slopes upwards, indicating increasing pipe length. Reflecting on the model, we can clearly see the minimum value of L is 2. This minimum occurs for any value of x in the interval from 0 to 2, inclusive. This means the house can be built anywhere between the water and gas points, and the total pipe length will always be the same, 2 kilometers. This is a very useful conclusion for the builder. We have successfully used the modeling cycle to solve a practical problem. In the next section, we'll dive deeper into linear models. We will now focus on the simplest yet very important type of mathematical model, the linear model. Two variables are linearly related if their graph is a straight line. This means the dependent variable changes at a constant rate with respect to the independent variable. The general form of a linear model is y equal mx plus c, where m is the gradient and c is the y-intercept. Let's explore this with an example. Suppose a taxi charges an initial fee of £4 and then £2 for each kilometer traveled. Here, the distance traveled, d, is the independent variable, and the cost, c, is the dependent variable. A cost of £4 for zero distance represents the fixed initial fee. If we plot these points, we see they lie on a straight line. The intercept on the c-axis is 4, which is the initial fee. The gradient, calculated as the change in c over the change in d, is 2. This means the cost increases by £2 for every 1 kilometer traveled. Therefore, the linear model connecting cost and distance is c equals 2d plus 4. This model is exact. It perfectly describes the taxi fare. We can use it to predict the cost of any journey. For example, a 10-kilometer journey would cost c equals 2 times 10 plus 4, which is £24. Now, what happens if the relationship isn't exact? In many real-world scenarios, data points might not form a perfect straight line, but they show a linear trend. In such cases, we use an approximate linear model. To use in CE, for instance, consider the number of customers at a new restaurant over time. If we plot the number of customers against the day, we might see points scattered around a straight line, but not perfectly on it. In Chapter 7, you will learn the formal method of linear regression, which finds the best fit straight line for a set of data. This line, like the one shown here, is an approximate model. It can be used to predict trends, but its predictions come with some degree of uncertainty. A critical aspect of using any model, especially an approximate one, is being aware of its limitations. One common pitfall is extrapolation. Extrapolation is the process of predicting values outside the range of your original data. While it can sometimes be reasonable, you must be careful. For example, if we use the restaurant model to predict customers on day 100, we get 650. But this assumes the linear trend continues indefinitely, which is unrealistic. A restaurant has a maximum capacity. The model is useful within its domain of proven relevance, but becomes unreliable beyond that. Let's work through 2 HL-level examples involving linear models. These exercises will help consolidate your understanding. First, consider a population of bacteria that doubles every hour. There are initially 100 bacteria. We will model the population P after T hours. This is a classic exponential growth problem. But what if we made a simplifying assumption to create a linear model? This is the essence of modeling. Let's assume the growth rate is constant. The bacteria grow from 100 to 200 in the first hour, an increase of 100. We'll simplify and assume this constant rate of growth of 100 bacteria per hour. With this assumption, the population after T hours is the initial population plus the growth. Our linear model becomes P equals 100 plus 100T. Now let's test our model by comparing its prediction after 5 hours to the true exponential value. Our model predicts P of 5 equals 600. However, the true population, doubling every hour, would be 100 times 2 to the power of 5, which is 3,200. The linear model is a very poor approximation in this case. It failed because our assumption of a constant growth rate was fundamentally flawed for this type of problem. This shows the importance of selecting an appropriate model type, which is part of developing the model in the cycle. Now, let's look at another common type of linear modeling problem. Henri takes 6 hours to clean a house alone, and Marcia takes 5 hours alone. If they work together, how long will it take? This is a work rate problem. To model it, we need to think about how much of the house each person cleans per hour. In 1 hour, Henri cleans 1/6 of the house. Marcia cleans 1/5 of the house. Now for the key assumption, we assume they can work together without getting in each other's way. This means their work rates can be added. So together, they clean 11 out of 30 parts of the house each hour. Let T be the total time. The fraction of the house cleaned in T hours is T times their combined rate. To complete the job, this fraction must equal 1. Solving for T, we get T equals 30 over 11, which is approximately 2.73 hours, or 2 hours and 44 minutes. This is a reasonable answer. The time it takes them together is less than either of them alone, and also less than half of the longer time, which makes sense if they are working at different speeds. We now move to a more complex and often more realistic type of model, the piecewise model. In many real-world situations, a single formula isn't enough to describe a relationship over its entire domain. Instead, the rules might change at certain points. A piecewise model allows us to divide the domain into subintervals and use a separate formula for each interval. Piecewise linear models are particularly common. Let's look at a water billing example. This graph shows the cost of water. Notice there are two distinct line segments. The first, for usage up to 25 kL, has a shallower slope, indicating a base rate. After 25 kL, the slope is steeper, meaning you are charged at a higher rate. This structure is best described by a piecewise model. Let's analyze the first segment. The points are 0 phi and 25 when 100. The gradient is 2. This means for the first 25 kL, the cost is $2 per kL on top of an initial fee of $50. For the second segment, the points are 25, 100, and 50 since 220. The gradient is 4.8. This means for any water used above 25 kL, the cost is $4.80 per kL. The increase in gradient reflects the higher rate. A very important type of piecewise function is the absolute value function. Understanding it is key for many HL problems. The absolute value or modulus of a number x written x represents its distance from 0 on the number line. Because distance cannot be negative, the absolute value is always non-negative. This definition leads to its algebraic form. If x is positive, its distance from 0 is just x. If x is negative, its distance is the positive version of that number, which we write as negative x. For example, h7 is 7 and h5 is 5. Because of this split definition, the graph of y xo is a piecewise function. It has a V-shape with its vertex at the origin. For x values greater than or equal to 0, it follows the line y x. For x values less than 0, it follows the line y equals x. Taking the absolute value of a linear expression always creates a piecewise linear graph with a V-shape. For example, let's sketch y in Basel backput plus 3 so. The critical point is where the expression inside the absolute value is 0, which is x equals negative 3. This is the vertex. For x greater than or equal to negative 3, the graph is y is x plus 3. For x less than negative 3, the expression x plus 3 is negative, so the graph is y x plus 3, which simplifies to y equals 3. This gives us the V-shaped graph. What if we have two or more absolute value terms? We can still sketch the graph by considering the critical points. Let's sketch for us. The critical points are x equals 0 and x equals 4. These points divide the x-axis into 3 regions. In each region, we simplify the expression. For x less than 0, both terms are negative. For x between 0 and 4, the first term is positive, the second is negative. For x greater than or equal to 4, both terms are positive. The graph is a piecewise linear function. It consists of 3 segments: a downward sloping line, a horizontal line segment between x equals 0 and x equals 4 at y equals 4, and an upward sloping line. The vertex points are to 0, 4, and 4, 4, and the minimum value of y is 4. Let's work through an IB-style problem to apply our knowledge of piecewise models, specifically to a distance-time graph for a triathlon. The problem states that a swimmer completes a triathlon with 3 legs: a swim, a bike ride, and a run. We are given the distance of each leg and the time taken for each. We need to sketch a distance-time graph to model the swimmer's position during the race. This is a perfect scenario for a piecewise linear model. The swimmer's speed, and thus the gradient of the graph, changes between each leg. A piecewise model allows us to represent this changing rate of travel. Before we draw the graph, let's identify the points that define the end of each leg. Since the graph is distance time, the distance value is cumulative. Point A is the start, so 0 saw 0. Point B marks the end of the swim. It's 36 minutes and 1.55 kilometers into the race. Point C marks the end of the bike ride. The cumulative distance is 1.5 plus 40, which is 41.5 kilometers, at a time of 36 plus 81, which is 117 minutes. Point D is the finish line, with a total distance of 51.5 plus 10, or 51.5 kilometers, at a total time of 117 plus 54, or 171 minutes. Now we can sketch the graph. We plot these 4 points and connect them with straight line segments. The gradient of each segment represents the average speed during that leg. Notice how the bike segment has the steepest gradient, reflecting the highest speed. Part B asks for any assumptions we made. Let's think. We assume the swimmer maintains a constant average speed during each individual leg. In reality, a swimmer's speed fluctuates throughout a race. But for this model, we've simplified it to an average for each segment. This is a reasonable assumption for creating a simple and useful model. Finally, Part C asks us to use the graph to estimate how far Alana had traveled after 1 hour. 1 hour is 60 minutes. We can locate 60 minutes on the horizontal axis, trace a vertical line up to our graph, and then trace a horizontal line across to the vertical distance axis. By eye, this appears to be approximately 12 kilometers. This visual interpretation is a valid method for answering the question. This problem demonstrates how to construct a piecewise linear model from given data, make and justify assumptions, and use the resulting graph to make predictions. We now move to our final core topic: how to find the specific equation of a model when you are given data points. Often we have a general idea of the form a model should take. For example, the height of a ball thrown into the air is described by a quadratic function. Our task then is to find the specific values of the coefficients in that function. The key principle is that to find a model with a certain number of unknown coefficients or parameters, you need at least that many data points. Let's demonstrate with an example. Suppose we want to find the equation of a quadratic function that passes through 3 specific points. We know a quadratic has the form y equals x2 plus bx plus c. This model has 3 unknown parameters, a, b, and c. Therefore, we need 3 data points. Let's use 1 R2, 2, 4, and 3, 12. The strategy is to substitute each data point into the general equation to create a system of linear equations. Using point 1 or 2, we get negative 2 equals a plus b plus c. Using point 2, 4, we get 4 equals 4a plus 2b plus c. And using point 3, 12, we get 12 equals 9a plus 3b plus c. This gives us a system of 3 linear equations with 3 unknowns. This system can be solved using various methods. In your IB exams, you are expected to be proficient in using a graphics calculator for this purpose. Let's demonstrate how to solve this on a calculator. We navigate to the Equation or Solver app, select Simultaneous for a system of equations, and specify 3 unknowns. Then we input the coefficients from our equations. The calculator returns the solution, a equals 2, b equals 0, and c equals negative 4. Substituting these values back into our general quadratic form, we find the specific model for the graph. Y equals 2x squared minus 4. This process is incredibly powerful for constructing accurate models from data. Now, let's look at another example involving systems of equations, but this time for a cubic model. The table shows the quantity V of air affected by smoke T seconds after a fire. We are told this is a cubic model of the form V equals AT3 plus BT2 plus CT, and we need to find the coefficients a, b, and c. The model VEAT3 plus BT2 plus CT has three unknown coefficients. So the three data points, 1, 2, 2, 4, and 3, 12, are sufficient to define the system. First, substitute the point 1, 2. This gives us our first equation. A plus B plus C equals 2. Next, substitute the point 2, 4. This yields our second equation. 8a plus 4b plus 2c equals 4. We can divide all terms by 2 to simplify this to 4a plus 2b plus c equals 2. Finally, substitute the point at 3, 12. This gives our third and final equation. 27a plus 9b plus 3c equals 12. Again, we can simplify by dividing by 3 to get 9a plus 3b plus c equals 4. So we have a system of three linear equations. Using our graphics calculator's solver function once again, we input the coefficients for each variable. The calculator solves the system for us, revealing that a equals 1, b equals -3, and c equals 4. By substituting these values back into the general cubic form, we have successfully determined the exact cubic model that fits the data. V equals t cubed minus 3 squared plus 4t. It's worth noting that this process also works for more complex functions. For example, if a model has the form y equals x plus x plus c, you would substitute your 3 points, and you would again get a system of three linear equations in terms of a, b, and c, which you can then solve. Before we move to practice questions, let's have a brief but important discussion. We've seen that sometimes in piecewise models, the function from one piece meets the function from the next piece. Other times, they do not. We would describe a function where the pieces meet at the transition point as continuous. A continuous model implies a smooth transition in the real-world scenario it describes. In our water cost example, the graph was continuous. The cost at 25 kL was the same, regardless of which formula we used. This makes sense. Your water bill doesn't suddenly jump up by a fixed amount when you exceed your allowance. It increases smoothly, just at a faster rate. However, a model can also be discontinuous. Here, f1 of a does not equal f2 of a. The pieces don't join, creating a jump in the graph. This is often called a step function. A step function would be appropriate for modeling taxi fares. When you get in the taxi, you are immediately charged a call-out fee. For 0 minutes of travel, the cost is the fee. For 1 second of travel, the cost is the fee plus the cost for the first minute. There is a jump in cost at the boundary of 0. The key is to use your real-world context to justify your choice. Does the situation you are modeling involve a gradual change or a sudden jump? Answering this question helps you build a more appropriate model. We have covered the main concepts of mathematical modeling in this session. Now, it's time to test your understanding with some IB-style practice questions. The time allowed for this competition is 75 seconds. Competitors receive a time penalty for every commenced 4-second period they exceed this time. For example, a time of 9.4 seconds is 4.4 seconds over, so it incurs 2 penalties. Question 1 asks you to model this situation. First, draw a graph of time penalties against the time over the allowed limit. Then use it to find the penalties for a competitor who is 12.1 seconds over. Question 2 gives a piecewise model for the height of a bouncing ball, h, after t seconds. The ball is dropped from a tower, bounces at 3 seconds, and hits the ground again at 7 seconds. You need to find all the unknown constants in the model. Question 3 presents 2 possible cost functions for a restaurant to order tomatoes. The restaurant always chooses the cheaper option. You need to construct a piecewise model for the total cost and then find the cost for 6 and 9 kilograms. Question 4 asks you to find the equation of a quadratic function that passes through 3 given points. This is a direct application of the systems of equations method we learned. Question 5 involves modeling the relationship between height and radius for cylinders with a constant surface area. You are given a graph with 2 data points and a general function. You need to find the constants in the function and then calculate the surface area. Take your time to solve these problems. You can pause the video now. When you're ready, we'll go through the detailed solutions together. Welcome back. Let's now review the solutions to the practice questions. See how your answers compare. For question 1, the time over t is positive. The number of penalties, p, is a step function. For 0 less than or equal to t less than 4, p is 1. For 4 less than or equal to t less than 8, p is 2, and so on. A graph of this is a series of steps. For a time of 12.1 seconds over, it falls into the interval between 12 and 16, so the competitor receives 4 penalties. For question 2, we use the boundary conditions and the peak of the second parabola. At t3, h must be 0, so 0 equals 5, 3.2 plus c, which means c equals 45. The pieces must join at t3, so the second formula also gives h and 0. The maximum height is at the turning point of the parabola h in t equals 5t2 plus dt plus e, which occurs at ta t 2 equals d past 10 equals d 10. Given the bounce lasts 4 seconds, the peak is midway at t e3 plus 4 2 equals 5. So d until 5, which means d equals 50. Now substitute 5h peak into the formula. The model predicts a peak height of 20 palmets. For question 3, we first find where the 2 cost functions are equal, which happens at x equals 9 kilos. Below 9 ki, supplier B is cheaper. Above 9 ki, supplier A is cheaper. The piecewise model reflects this choice. For 6 kilo, which is less than 9, we use supplier B's function, giving $30. For 9 kilo, either function gives the same cost of $36. Question 4 is a repeat of our worked example. By setting up the system of 3 equations and solving it using technology, we find A equals 2, B equals 0, and C equals -4. The quadratic equation is y equals 2x squared minus 4. For question 5, we substitute the 2 given points into the equation h equals a r plus. This gives us a system of 2 linear equations in terms of a and b. Solving this system gives a equals 28 and b equals 1. The equation is h 28 plus r. The constant surface area for these cylinders is the area when h is 16 and r 2, which is approximately 226 square units. This concludes our deep dive into mathematical modeling. We have covered the fundamental cycle, different types of functions, and how to use systems of equations to find model parameters. Remember, the key to success in IB mathematics is practice. Work through more problems, especially those from past papers, to solidify these concepts. We hope this video has been a helpful resource in your studies. If you are looking for more personalized support, Dart Tutors offers expert tuition in IB, A-Level, and IGCSE curricula. Visit our website or contact us directly to learn more about how our experienced tutors can help you achieve your academic goals. Thank you for watching.